All right, guys, so we are recording. We're gonna get started. Okay, so let's switch over to let's switch over to the bright space. All right, 365, section 1. So let's do a quick recap of where we are. Um, so matrices and vectors, right? You guys have gone through all these problems by now, hopefully, twice at least. Right, so remember, you don't have to submit these as homework, but I strongly recommend that you go through them. If not, by the end of class today, you will be very shocked, right? So because we are going to start using these in the algorithms, right? And so you'll see the reason why I asked you to practice all these problems. So again, remember, this is not a homework, but you should be doing all of these problems, replicate and developing muscle memory. We covered the machine learning pipeline and we went over word problems on Monday. So hopefully I did at least 2 of those. I'll probably try to do maybe 2 more as when we have time. You don't have to submit any homework with that, but it's just a procedure to go from any problem to format your data and everything, answer all the questions relevant to building a machine learning model. Then we've covered the module on Weka, so you guys have an actual homework assignment for this one, which has been given. Instructions are provided, and I believe it's due in about a week and a half, right? So just check that out. All right, so today we're starting the first set of algorithms that we're going to cover in this course. As you know, there's a lot of algorithms that we're going to cover. We have a very tight schedule for this, right? So we're going to cover the first one today, which is KNN. The K nearest neighbor algorithm is the easiest one to understand. My goal is to cover also Hopfield, in the coming weeks, Hopfield networks, which if you have been reading the news, you probably know that John Hopfield got the Nobel Prize in physics for that one algorithm. So they created it back in the 80s, I want to say. So we'll go over that one and you'll see what gets you a Nobel Prize if you had done that in the 80s, right? So it's a very powerful idea. And it starts to lead into this idea of neural networks, right? Then we're going to cover, my plan is to cover the perceptron, which is the very first neural network back in the 40s. And then after that, multi-layer perceptron, all of these algorithms written from scratch in Numpy, right? So that's the fundamentals of the course. And that gets us close to about, week 6. I remind you that you will have an exam on week 6. And then starting on week 6 or 7, we're going to start looking at deep learning, starting with linear regression, logistic regression, multi-layer perceptrons again, but from the perspective of PyTorch, a very powerful library for neural networks. And we'll talk a lot about that until you build your deep learning algorithms, right, in PyTorch. And then that gets us to week 12, which is the exam, a second exam. And then after that, the third of the class will be special topics such as something called transfer learning. We will look at something called a ResNet. And throughout, there will be other little topics that I need to cover, such as the metrics and everything in more depth. Does that make sense? But today we're just going to code, okay? I don't know that there will be necessarily a homework for this one. I'll think about it, right? But certainly today is your first algorithm that we're going to build in Python with NumPy from scratch. Okay, so we'll do that in a second. And it's the K nearest neighbor algorithm. I've given you some ideas of this on Monday when I started talking about the vector space model and this idea of representing samples in a vector space as points. And then it's a geometrical representation. And then we have these properties of distance, metrics, and all of that. Got it? All right, so the reading starts at this point also. So you now will have a lot of reading to do. All right, so basically, I'm going to show you where those things are. So we are currently in this module, KNN, K nearest neighbor algorithm. And I provided all these links for you to read. All right, so some of these are just the Jupyter notebooks. As usual, the code is going to be in my GitHub. So I'll show you where the code is. That's what we're going to do today. But I provide a reference. Reading through these PowerPoint slides, so these are things I've done in previous years where I take notes and just dump them here so you can read through this. There's this document, the Euclidean distance. So obviously all of this is going to be in the code, right? Because it's the algorithm. So the algorithm is going to take some data and we're going to build a machine learning algorithm and evaluate performance, essentially. This algorithm you can use for a problem, right? You know, sometimes you don't need neural networks for everything. There are problems where a KNN may be more than enough, okay? So, but that's what we're going to cover today. But, you know, we're going to be using something called a Euclidean distance. So I strongly recommend you go through these notes. This is just an overall description of KNN. I recommend that you go through that. The code is going to be provided here. I provided a Jupyter notebook in Brightspace here. These two, read through them. They're probably just versions. I always do that. Like I'll write several versions of a program, but they're all about KNN, that one algorithm. So there's actually three, if you notice. This is just what I wrote in 2023. So I may have tweaked it a little bit. Here's your additional reading. Okay, so I'm going to click on this link. Read this. Okay, this is a blog post I wrote. It's kind of a rough draft, so it's, you know, excuse me if you find a few misspellings here and there. Feel free to point them out and I'll fix it. All right, but this is, you know, meant for you guys to have something that's free that you can read through. This is a lot of the material that we will cover, you know, things like code issues. Definitely read through it, as I don't have time, unfortunately, to cover every single detail, but it's here. Okay, so just read through it. Performance metrics, you've seen this already, right, in Weka. That's why I show you Weka. It's the same metrics. Eventually, we'll have a lecture where we drill down into the formulas for all of this. But, you know, this is the code, object-oriented programming. Make sure you read through this, as most of the code going forward is going to become object-oriented in that style of object-oriented programming. Don't be scared by it. You'll love it. This is the only way that you can actually build complex neural networks and, you know, a ChatGPT. There's no way that you could write, I don't know, 20,000 lines of code if you didn't use object-oriented programming. Okay, so at least to start to understand it. Later on, when you develop your skills, okay, write it in C, sure. But for now, you know. So read through this. This will give you a really very simple background. We will use this format in about starting from week 6, just so that we can have, basically think of it this way. I like to give you these like templates, right? And then once you understand that template, then you can start to build your own machine learning algorithms using that basic logic. So think of the template as the machine learning pipeline in a sense. So the performance metrics, as I said, I'll provide some of the math behind this, but you can see the equations there. And we'll need to talk about that later. This is essentially the function we will be using to evaluate performance going forward, and I'll use it in a lot of classes. So you just have to understand this once and then reuse it. And then there's things like plotting performance, so read through that. Optimization, I do have to do a class related to this, but this will be later on in the context of neural networks. How do neural networks learn? So we're going to see a lot of the really cool ideas behind this. And I have some links here that we will cover later. These are links to Jupyter notebooks that have the information. Logistic regression, we'll cover that later. Neural networks, this is just a quick intro. You can see this is the topic of today, KNN. So obviously some of this reading is related, it will be related to other things in the future, but just start here and try to grasp this really well. So we're going to talk about the KNN algorithm. I'm not going to read this paragraph for you. You can read it. I'm just going to go, dive into the code, but you can see the code is provided here and it's not that long. Some really nice, I really like history of math. I'm kind of a nerd that way. And so this is just some of the interesting history of the math behind KNN goes all the way back to the Greeks, Pythagoras. So you might be surprised, right? You probably learn about this like in elementary school or something, and it literally goes back to that, right? So back to the Greeks, and and so read through that, and then here I've provided basically the essential connection between the math that we will be doing in our KNN algorithm and how it ties back to Pythagoras and all of that. So read through that. Yeah, and then this goes, this covers other algorithms. So XGBoost is certainly one of the algorithms that we will cover later in the semester, at least as a black box, because it's an extremely powerful algorithm that you should know about and just throw at some problem later on. So it's definitely it's a tree-based algorithm. Yeah, and that's it. So just read through these. These are your reading assignment. And you should start going over all that material. Make sense? All right, so now that we've talked about that, let's go ahead and start coding our very first algorithm. This is the easiest algorithm that we can code, I would think. Came here as neighbor. We're going to build it from scratch. We don't really need, anything, any power libraries, specialized libraries or anything. We'll use NumPy just because, as you have seen, it allows us to do certain efficient math operations, right? But yeah, essentially we're building it from scratch. All right, so let's go ahead then. And are there any questions, I should say, before I begin? All right, great. So how are we going to approach this? Let's go ahead and I'll start Anaconda. And so that would be the prompt. All right. There. So I'm going to navigate the desktop. So essentially, whenever we do a machine learning algorithm, we have some data that we want to model. It could be the iris data, for instance, and we just want to take measurements of iris flowers and say if it's a setosa, virginica, versicolor. A lot of the time, I like to create data randomly initially. Like I just, create some data randomly, small data set, build the architecture, test it out a little bit, and then start adding like the data set, et cetera, and dealing with that. And then, of course, as we build a model, we need to evaluate it. So a lot of these steps are going to apply to all the algorithms we're going to do this semester. So let's navigate into the folder for this course. So that should be, I guess we haven't, did I create a folder for this? 360, oh, here it is. No, I didn't. CD ITS 365 2025. Okay. CLS DIR. All right. So tensor operations was the first thing we did, right? And you guys have done those 70 problems. Now we're going to implement the KNN algorithm. All right. So now I need to do conda environment list. And we're going to look at the different environments I have available and just pick one. Yeah, this one, Py30. So I guess I'm using Python 3.8, ITS 365 S 2025. So let's do that one. So conda environment list. Conda activate Py38 underscore IT. Yes, sir.
We were.
Was that what it was? Which one then? Oh, this top one? Yeah, I remember now. Yeah, thank you for that. I appreciate that. All right, so then it would be Pi 37. Yeah, good catch. Pi 37, 2025, ITS, ITS 365. All right. So okay, great. So we start the environment. We're in the folder. So now I'm going to do Jupyter Notebook. Jupyter Notebook. Okay. So you guys understand that these are like levels of abstraction, right? We use Jupyter Notebooks, we use Numpy just to kind of understand the algorithms. But just like with everything, there's a hit, obviously, if you use Python versus something like C, C++, right? So you guys take C, right? You take a C course or C, C++, and in that course, you learn how to program. It's a little bit harder, but that language is way more efficient. So anything that you do in that language is super fast, right? Versus Python, Python is essentially an interface to C. So I don't know if you know that. For instance, the NumPy libraries are written in C, but we are still using Python. Okay, so it creates a little bit of an overhead. So we'll continue to talk about this idea later. You could implement, what I'm trying to say is you could implement a lot of these algorithms in C, C++. There's no reason why you couldn't do that. It would just be a little bit more challenging, right? And so traditionally what is done today is that you learn NumPy, you learn either PyTorch or something else. You learn the algorithms. A lot of that is good enough for you to do quite a bit. But if you were building an application that needs to run really fast on the phone and be very competitive, you're probably going to start writing it in C. Does that make sense? You want to create the fastest solution. Yeah. So anyway, so we are not going to be writing in C in this class, but just be aware of it. All right, so I've created the environment. So now let's go ahead and start a Jupyter Notebook. Okay, and the idea for today, my goal is to just solve KNN. That's it, okay? So the way that I start these algorithms is I'll usually just go over like the main functions, establish the pipeline, think a little bit about the data, the shapes. Then we're going to drill down into every single function. Something won't work, we'll have to fix it. And then finally, do the training, measure performance, and we're done, okay? So that's kind of the idea. So one of the first libraries we will need, I don't remember what libraries I've installed here because it's a fresh connection, but I believe, or environment, but I do believe we had NumPy. So usually the syntax is you do import NumPy and then you can say as np. I could say as np3. I could say np Purdue, whatever you want. You're just giving it a handler name just so that you can control it. The tradition is just to say import NumPy as np. Okay, so I'm going to go ahead and run that. Give it a second. It ran fine and fast enough. All the code I'm going to use this semester is always on the GitHub, so I will always provide it. As I said to you guys, I rarely will ask you to write a program from scratch, an algorithm, but you do need to know how to modify them, right? And to read through them. Essentially, because you might have another data set, right? That doesn't look anything like Iris. And so you need to load that data and make it available. That's what the word problems are for. To arrive, remember in the word problems, you would go from some scenario to X and Y. And we want to know the shapes of X and Y. And you will see here in this code and most of my examples going forward, there will always be an X and a Y. Okay, so that is kind of, if you can get to that X and Y, then you can plug it into all these algorithms and it'll work. Okay. All right. So as you can see, this is just so in case you don't know, this will be the GitHub for this course is this one. So it's always going to be on it's pinned basically to my GitHub. It's the one that says Machine Learning Foundations, titled the same as the course. So you can download the zip or whatever, and it's perfectly fine. All right, so these are a lot of the algorithms that I've covered throughout the years, but I always start essentially with KNN. So I have several versions of it. So let's just take a look at probably KNN NumPy 3. And we're going to think about, see, we have to understand what this Euclidean function is doing, right? So this is an example of that. So actually, KNN NumPy 3 just has the Euclidean function. So let's look at 2. Right, so this is a more complete version of it. Okay, so I'm gonna go through it. And we're gonna think of the ideas. Okay, so essentially all we need is NumPy. We have a Euclidean distance, which is the thing in a vector space that allows us to measure the distance between one point and another point. And that's how the algorithm works. We have the data section, and then we have a predict function. This is called a lazy algorithm because in neural networks, for instance, you give a lot of data to the neural network. The neural network has these things called parameters. And as you're training that neural network, those parameters are being updated. And then once the parameters are updated, they go from having random values to having actual valuable values, right? And so once that's done, then now you can go ahead and use that model for other problems in the future. With KNN, you don't do that. This is a very simple algorithm. It's just based on geometry, essentially. You don't have weights. You don't have weights that are being trained or parameters, right? Instead, every time that you use KNN, essentially it's learning at that moment. So that's why it's called lazy, and you will see that. Okay? Because all it's doing is it's measuring the distance between. So one good example is actually this room, right? This room is a three-dimensional space. Each of you is a point in this room. And it's based on the X, Y, and Z coordinate. So basically, if that's the Z axis, you're all kind of at the same height, right? Z. So we can almost ignore Z and then just go by X and Y. And then X, you have an X and Y, you have an X and Y, you have an X and Y, and so on. And using that information, I can tell that you two over there, right, are closer than you and say you. That's essentially what we're doing. So we're going to have a data set of examples, and then let's say a new student comes into the room from another class. So you guys are the train set, and then a new student comes in, and that new student is the test sample. So what you're going to do is if the student comes here, the student is going to, right, stand there, and now assuming this three-dimensional space, you can measure the distance between that student and all the students in the room. Do you guys see that? And now you have, let's say that there's 30 students in this room. So now for that student, you have 30 different distances. And then once you have those 30 different distances, some are longer than others, right? So like you are probably the closest to the student if they're standing there. So that's the shortest distance. And then that student over there is probably the longest distance. So you have some distances that could be at, let's say, 6 feet versus, I don't know, like 15 feet, right? So you have that. And then what you do is you sort those distances from shortest to longest, and then you just grab the 5 shortest. And once you grab the 5 shortest, you look at the label associated with those 5 people. So essentially, if the student was standing here, probably the closest students would be you two, maybe you. You see that? So that's 3 distance, right? And let's say that the class is wearing a cap, not wearing a cap, right? So that student, would look at you 3 and your classes not wearing a cap, not wearing a cap, wearing a cap, right? So then what label do you assign to this new student? Not wearing a cap, because 2 don't have a cap and 1 has a cap. He's got a cap over there. So what if now 1, 1, 1, 1. So 2 would have a cap, 2 would not have a cap, and that would be a problem, right? Because you have a tie. So that's why you always want to use uneven numbers when you make the decision. And that's the whole algorithm. Your first machine learning algorithm is just that. We will implement this obviously in code, but that's essentially the idea. And the other thing I told you about, if you remember, is that yes, we can visualize only up to 3 dimensions, but this works for samples that have 20 features, right? And remember, each feature represents an axis. So it could be a 20-dimensional space, a 1,000-dimensional space. It does not matter. So if we do iris, iris has 4 features. So it's like saying it's had an X, a Y, a Z, and a K, a 4th dimension that we can't view, but mathematically, there's that point lives in that space that's 4-dimensional. Do you guys understand? So that is the KNN algorithm that I want you, that we're going to implement today. Any questions about any of that? Make sense? All right, great. So now let's go ahead and implement the algorithm. So notice it's called K because KNN, the K nearest neighbors. If K is 3, 1, 2, 3. You guys are the 3 nearest neighbors. 1, 2, 3, 4. If it was 4 or 5, maybe the 5 of you closest. If the sample moves over here, then now those 3 students probably are the closest. And so that's how it works. All right. Just keep in mind, doesn't just have to be coordinates, right? It could be the axis. We could be organized by age, and things like that. So it can be lots of things. Whatever you can use as a feature as a number. So let's do this one first. So K equal 5. Right? So I'm going to rename this as KNN, your first algorithm. I want to do the iris data set for this one for sure. So we want to think. So you want to think in terms of machine learning. So you always want to think like this, which is consistent with what I said with the word problems. You always want to have an X and a Y. You want to print out the shapes and so on. Okay? All right, we're going to need to define the Euclidean distance. We're going to need to define this. And we're going to think about the logic of this. So the first thing, we're going to create a function. Actually, let's start here because this is where the algorithm would begin. Let's go down here. And let's think a little bit. So initially, we'll have an X and Y, as we will learn later in the semester, or not later, today. We're always going to split this X and Y into actually X train, X test, and Y train, Y test. And the reason we do that is we always want to evaluate our model. So we're going to take some samples that we use to train, and then we're going to leave some samples that the model hasn't looked at, and we're going to use those to evaluate how good our model basically is. So I haven't created that yet, but we will. But essentially, we're going to have an X test data set. So I can write that here. So we're going to have an X test data set. We're going to have, let's just X train data set as well. So the X test is the test sample. So we're basically giving those to the model, and the model is going to tell us what that sample probably is given what it knows. So then what we do is each one of these samples, we can iterate through it. So for test X and X test, and we just give it to some function called predict in this scenario, right? So the predict function will take every single test sample. So let's say this X test has 30 samples, then individually we grab the first and the second and the third. We're going to give it to the predict function, okay? And the predict function is essentially where we implement the KNN algorithm. So I'm going to do, instead of predict, I'm going to say, or actually KNN predict could be a good name. KNN predict, right? So then here I'm going to just going to copy this. All right. KNN predict, it takes test X, colon. And now what do? Now we have to take this test sample and compare it to all the samples in X train. You see that? So that's the example. So X test is the student that came from the outside of the room. And now we're going to grab every sample in the room, and that's X train. So let's take a look at what we have here. So first of all, the first thing we're going to do is this part. So we say here, calculate distances between test X and all data samples in X train, which is the other part of the data set. So how do we do that? So if you look, we're going to create a list called distances. This here, whenever you have a for loop inside square brackets like that, what is that called? You guys surely have seen this. This is called a list comprehension. All right. It's a very nice feature in Python that you really want to get used to. So it's equivalent to this. So this is very familiar to you. For X in X train, print X. You're familiar. Everyone is familiar with this, right? We all know how that works in multiple programming languages. But sometimes this can be, it's not, we basically want to write it in one line and have this return a list conveniently. So what we do is instead of writing it like this, we say for X in X train, which is the same as this one here. And then this print X is right here, basically. We put it in front. And what's going to happen is each of those X's is going to populate that list. As we iterate through it, boom, it gets appended to that list, essentially. But we can do things to those X's. So in this case, if you notice, take this out. So if I just leave it like this line of code is exactly like this line, or these two lines of code. They're basically the same thing. But what I want to do is for each one of the samples in X train, I want to compare them to the sample that I'm bringing in, test X. So test X compare somehow to the X that's coming here. What's the comparison that I need to make? I need to calculate a distance between them. There are several distances in a vector space. The one that we're going to use is the one called a Euclidean distance, which is based on Pythagoras. So that's why I plug this in here. So I'm going to call this function, and I'm going to provide to it two arguments. Test X, which is the test sample I gave it, and then X, which is the samples in the train set. Measure the distance. Once I have the distances, sort them, pick the 5 or so shortest distances, and look at the label associated with those 5, and that's it. That's KNN. Super simple. Make sense? All right, excellent. So this part is done. Obviously, what do we need to define? We need to define the Euclidean distance. This Euclidean distance is where those 70 problems that you did at the beginning of the semester are going to start to help you, because it uses those matrix multiplications or operations, etc., to calculate the distance, essentially. So let's define this function. So I'm going to do define Euclidean distance. It takes two parameters, actually, two arguments, colon, and of course we need to define what this is, but I'm going to leave it there for now. So I have my function, and let's continue to think. We can come back to this later, but let's just continue to think about the algorithm itself, right? So we've got the distances here. So now let's say that there's 50 samples in the train set, and then you have one test set. So this list will have 50 distances. Do you guys see that? One for each of the samples in the train set. The next step is So it's going to look something like this. Now we want to do this part here. I'm just going to copy that. So here we are going to sort by distances and return the k closest neighbors. So k is going to be the 5. We're going to use a function called arcsort. You can see that. So we're going to use np.arcsort, right? So like sorting an algorithm. But what's really nice about arcsort is that we have distances in there, right? But we're not going to return distances. We're going to return the index of the distances. And that's going to be very convenient. Do you know what I mean by that? So think of a list like this. So I have a list where it says maybe 32, 4, 5, 18, right? But the index is actually 0, 1, 2, 3, right? So it's going to sort them. So when it sorts them, it would be 4, 5, 18, 32, right? That's sorting the values. But it returns this thing sorted, but it only returns the indices because we don't actually care about the value. What we want to know is which ones are the closest. So what we would get with arcsort is what? We would get 1, 2. That's interesting. 3, 0. Do you guys understand? Yeah. So I sorted them, but then it's only returning the index of them. Okay, because if we compare, so 1 is what? 4. 2 is 5. 3 is 18. And the last one is 32. Yeah. So like that. And it'll return the indices. And then with these indices, then let's say we just want the shortest ones, then we would just look for 1 and 2 basically, and those are the same. Questions? All right, so let's go ahead and do that. All right, so it'll take the distances here, which is going to be all the distances. We grab them and we apply the function np_arcsort. And that would give us all the distances sorted. Now, if you notice, then we have this little thing here. So what is the meaning of that? So when we do this operation, what that returns is essentially a list, right? A NumPy array, okay? And we know that when we have a NumPy array, we can apply to it slicing, for instance, or indexing, right? So that's what this is. If you notice, this is essentially slicing, which is one of the problems that you had to do, right? So slicing, if you remember, uses this notation. So we have a list, and now we're saying that we're going to slice out that from this, right? So what are we doing here? What does this mean? You should know this by now, right? When we have a colon in NumPy or PyTorch even, it means a range, right? And then so what's this range essentially? All samples up to 5. The first 5? Yeah. So yeah, exactly. So remember, if we say 2, then it starts at 2. But if we don't include an index in this position, then it means from beginning. But because these things are already sorted from shortest distance to highest distance, then we have the shortest at the front. So we can say, yes, start at the beginning up to k. And k is 5. So essentially, if we have 30 in there, it's going to give us the first 5, which is exactly what we want, the k nearest neighbors. Any questions on that idea? All right, seems like it makes sense. Okay, so we've got that part done. So let's just add it in there. That's the KNN algorithm. And now that we have the k neighbor indices, right, we want to take a look at the next part. So I'm going to copy this one here, and you can see we're almost done. So now it says we're going to extract labels from Y train. So one thing that you have to remember is the vector Y is aligned with the matrix X. So if I grab sample 3 from X, I know that its corresponding label is row 3 of Y. If I grab row 7 of X, I know that its corresponding label is 7 of Y. Did you see that? So by grabbing, this indices, I know exactly which label I need to get. So we extract the labels from Y train. So how do we do that? For I in K neighbor indices, which are these, which are the 1, 2, 3, let's say, indices. And now we just index Y train to extract the labels that we want. And we have then our labels here. Got it? All right. So, and that, believe it or not, is essentially the whole algorithm. At this point, we have the labels and we are able to do machine learning. You see that, guys? Pretty easy. All right. So now let's test. That's the whole algorithm. That's the whole algorithm. Everything that comes after that is just like some averaging and things like that, but that's the whole algorithm. So now what I want to do is I want to try this out with values, right? So we're going to use the iris data set, right? So we're going to bring in iris. So I think I usually have iris here on my desktop. Oh, here it is, iris. So usually actually reading the files sometimes is more difficult than anything else. So we are doing this one and I'm pasting that there. You guys see that? So if we go back to the GitHub, it should be there too. I'm pretty sure I did that. There it is. You see that iris.csv? That's the file that you need to download. Let's take a look at it. We have a few problems here. Weka would have taken this file with words as labels, but in NumPy, that's not going to work. So we're going to have to change that to numbers. So Setosa, Virginica, versicolor, that's going to become 0, 1, 2. Okay. These values are fine, and we're not going to need the heading here, right? We know we got 150 samples. Yeah, 151 with the header. And we have 4 columns for features, 1, 2, 3, 4, and the labels, which are these species. So we're going to take the first 120 for training purposes, and we're going to leave the last 30 for testing. And then we're going to measure performance. And that's the whole machine learning pipeline. Any problem that you have, if you can put it in terms of this CSV, then you would be able to solve it with KNN, the algorithm I just gave you. Got it? All right, so let's implement this. To read in this file, I'm just going to use a standard library. So we may need to use pandas, but NumPy also has its own functions. So let's take a look. So KNN batches. So there we go. It's exactly what we need. But it's pandas. Have you guys heard of pandas before? You must have in 265, right? That's one of the things that they showed you. Awesome. Do you want to say something? Did you like pandas? Yeah. That's excellent. Yeah, pandas is one way I would say pandas is like Excel and SQL but Python. Yeah. Yeah. So pandas is really great. So if you've never used it, definitely learn it, because a lot of the time, actually, when you're dealing with a data science problem, you're spending all your time in pandas just to arrive at that X and Y, and then everything just works, right? So it's kind of how it is. But yeah, so let's go ahead and use pandas for this one. So I'm going to read in the data. I'm going to do that probably here, I think. I mean, I guess I have my habits. My habits are I always put the libraries at the top, then I put the reading of the file at the top, and then after that, follow the algorithm. So I'll be consistent. Oh, parameters would go here. So actually, I'm going to add it here. Okay, there we go. So I'm going to use pandas. So that means we need to do import pandas as PD. Similar syntax. So I can't remember if this is installed already, so let's just run it. It says it's not. So what we're going to do then is exclamation pip install pandas. Just like that. Go ahead and run it. Give it a minute. All right. So this is white background now. You can see no errors. It says successfully install pandas. That's exactly what we want. So I usually just leave these, but comment them out. So that way, when I'm looking at this Jupyter later on, I know which libraries I needed, etc. All right, so let's try it now. All right, so it finished. No errors. Perfect. We have it. K is set up. So iris.csv, that should be the file. So that shows here, iris.csv. And let's take a look. So it had a header. We saw that. So then I'm going to say header none. And this is one way of doing it. I'm providing the file. This just implies that file in the current working directory and read it as a CSV. And it's going to be a data frame. So it's a pandas data structure, not a NumPy data structure. So we'll have to make some changes. All right, that's a good sign. I ran it, no issues. So now we can take a look at our data. So I'm just going to do df, hit run, and there we go. That's pandas right there. We have our data set. Pandas is really nice, well formatted, all of that. It says we have 150 samples, 151 rows, 5 columns. We can see already there's a problem. The header is stayed there. So we'll have to solve that. And definitely we have to change these variables to numbers because we need to convert this to NumPy. All right, so let's take a look at the script here. I think we were looking at. Oh yeah, sure. Which part? Yep. So we need to make some modifications to this. I'm not going to normalize or scale anything right now. We're just going to focus on making this so that it'll fit in a NumPy array, and we want to train our KNN out. Okay. So we did this here. We can see it looks exactly like that. So data frame, label encoder, all that good stuff. All right, so I'm going to start processing. So the operations that I'm going to do right now are operations that are very similar to the first problems you had to do at the beginning of the semester. So the first thing I want to do is I'm going to grab this. So this is going to be an example of slicing, for instance, because as you can see, the X matrix is the first 4 columns. The Y matrix is the last column. We need to split that up. That's just a standard procedure for everything we're going to do all semester. Okay, so let's go. So let's take a look at it. So currently it's called df. So there's various ways of doing this, but in pandas, you can do df.loc, and then we can do 1 to the end, and from the beginning to 3. And then dot values. So again, you need to understand what's happening there. That's the magic, right? Oh, pandas. Imagine if you had to do this with 2 for loops. That would not be fun. With pandas or NumPy and with slicing and indexing, you can do it in one line of code. So remember, the first thing indicates for DF, the whole data frame here, right? The whole data frame, we say what? As far as the rows, which start at 0, I want all rows from 1 until the end. That's this part here. So that allows us to skip row 0, which has the headings. Memorize and understand what they are, but you don't need to include that in the model. You just need to know what it is in your own head. So from 1 to the end. So that's all rows starting at 1, excluding the first one. Then as far as the columns, you only want the features, right? So the features are going to be from the first column to the third column, or the column index is 3. So that means this column, this column, this column, this column, but not the last column, because that's the labels and that should be in Y. Okay, so I'm going to do that, and then the dot values just gets it out of X basically. So let me take that out for now. Let's run it first to see if it works. Okay, it ran, no issues, perfect. Now I like to look at the data. It's a big habit I have of just always looking at things. So now run X. And you can see X now does not look like the pandas data frame anymore. It looks more like this. So you have numbers, 5.1. But what if your data set is really big, right? So this is actually not, when your data set is really large, doing this doesn't actually help much. Instead, what we probably want to do is look at x.shape. That's a much better. All right, so now we know this X is 150, 4. So it's got 150 rows, 4 columns. That's my X. We also want to look at the type. So X, or this is setting the type actually. So I think type is what? I think just the word type and then X in it. Let's see if that works. Yeah, there you go. So that's a nice confirmation because it says this is now a NumPy array and not a pandas data frame. That's really important because you wouldn't be able to do NumPy operations on a pandas data frame. You got to convert. So this is one thing. Our pipeline, when we're dealing with data, is going to usually go pandas to NumPy to torch to NumPy to torch, maybe to pandas at the end. You know, pandas is more for processing and looking, and then NumPy and torch are actually going to be for the algorithms and training. All right, now that we've done this, we're going to set the data type. So we know this is a NumPy array, so that's a data structure. But now we can also set, if we want, the data type of the data as float. You can set it as float 32, float 16. This is actually really important because that value determines how big the variables are, how much RAM memory is being allocated for that value. So if you have something like ChatGPT or DeepSeek, those really large models, you know, each one of those variables being 32-bit, it's going to create 7 gigabytes of a model in your computer, and that's going to run pretty slow. So what they do sometimes is they just make all of those 8-bit. And if it works, then, you know, that's better because it's going to run faster. You're going to need less memory and so on. Okay, so really important. All right, so that's that. We did X, right? Great. Now we're going to repeat the task with Y. So let's see what happens. So Y is, remember, it's all coming from here, and we're doing slicing, right? Like slicing a cake. So we slice these 4 columns and that other column. So now I'm going to do the same from dataframe.loc. What does that mean? From row 1 to the end, excluding row 0, which is the headings. And then this means what? No range, right? So we're saying just that column. We can also provide a list of columns. Let's say that we wanted columns 4 and 7. We could do that by providing a little list and separating the indices. But in this case, all we want is column 4. And then we convert it into values. So I'm going to run that one, work just fine. I can print Y. And you can see we have a problem. We've got the labels, but the labels are strings, and that's not going to work in either NumPy or Torch. So we need to convert that to numbers, integers usually. Okay, so there's a lot. You could do that manually, of course, but there's a very handy library for that. One good idea would be to print the shapes, which I recommend. So we can do this one here and just see what the length of Y is, 150. Or even better, you can do Y dot shape. That dot shape is like your best friend. Okay, I can't stress that enough. I would say 3-4 years ago, that was not available. And it was much harder to build neural networks. And now that's available, and it's super useful. Okay. So 150, if you think about it, this could also be 150 comma 1. So there's a difference actually between 150 comma and 150 comma 1. Essentially, it's the same data, but the data structure is a little bit different. And especially in terms of matrix multiplications and things like that. So we'll learn later that sometimes we want to change this to be 150 comma 1. All right, so now, but for now, the thing we want to look at is how do we convert these words into numbers, right? And we have a very nice feature, a very nice tool called the label encoder from sklearn. So that's another library that we're going to use sometimes, sklearn. Okay. I definitely don't like it for you guys to use sklearn for modeling. I think that's not what you should be doing. But for processing, the other parts of the data pipeline definitely use sklearn. Because I think you should be learning, how to do things from scratch or using Torch or something like that, which is state of the art. All right, so now this function label encoder is from sklearn, so I'm going to need the sklearn library. So I'm going to scroll up here, and you can see there's sklearn, but we're going to, actually, I'm going to need a couple of things. Let's do it one at a time so it's not confusing. So first, I'm going to grab this one. All right. And I'm going to just add it to my libraries. I'm going to say import sklearn. It's an old library before PyTorch. So there was a time when this was the go-to, but obviously we have better things now. But this is still powerful and widely used. So from sklearn.preprocessing, we want to import the label encoder, which is the function that can help us to easily convert from strings to numbers. So let's run this one. And as you can see, sklearn is not there. So we need to install it. So I'm going to do pip install. And actually the words for this are, I think, scikit dash learn dash. Yeah, so it should be that. So let's run that one. Let's give it a minute. Yes. Yes, go ahead. Here. There it is. And you can see that it installed correctly, right? No errors, nothing red, and it says successfully installed. So everyone should be here. Good. All right. So we have it now. So I'm going to just comment it out. Okay. Run that again just to save it. Now I'm going to run this. It's thinking. All right, it finished, no error. So that tells you that we have it. We have our label encoder. So now let's proceed to encode our strings into integers. So the way it works is pretty straightforward. Everything is object oriented in these libraries. So you instantiate a label encoder. So you do label encoder LE. That's your object. And then you're going to use it. So we say LE dot fit transform Y. So essentially, we're going to give it this whole thing here, right? And it's going to read it, and it's going to say, okay, there's three classes, there's strings. Okay, that's easy, 0, 1, 2. That's what it's going to learn. And then we just apply it to Y, and it's going to convert it, right? So let's take a look at that. So as you can see, we basically train the model, fit, but we also transform. So sklearn has this thing where you can do fit, transform, or fit and transform at the same time in one shot. So it's going to convert the Y to numbers now. Done. Print Y. And you can see the labels are now zeros, ones, or twos, which is what NumPy requires, essentially. Do you guys see that? So that's it. I mean, so we've got our X and Y. And now, hopefully you believe me when I said, in the word problems, get to X and Y. And from there, you're going to go on. So now we can do X dot shape and also Y dot shape. We have our matrix and vector. And so we run them. So we have 150, comma 4. That's the X matrix. And 150, comma 1, or just 150, which is the labels. And as I was saying, if I grab row 7 of X, the corresponding label is going to be 7 in Y. Do you see that? If I grab row 13 of X, which has 4 features, then the corresponding label is in 13 of Y. That's why when we use that arc sort, we get the indices so that we can slice them out from Y. Any questions about that? All right, great. So we are almost there. So now that we have X and Y, the next step is we need to proceed to create X train, X test, Y train, Y test, given that we're going to use, some of them to train about 80% or so, and then the rest to test the model. So again, for that, we can use sklearn. Scroll down. So there's my data. We did the label encoding, and then this part is actually super easy. From sklearn, and this is something that I always use actually, even at the end of the semester, we'll be doing maybe a ResNet or something, and we may still be using train test split. So this function, the key function here is train test split. It's from sklearn. What do we give it? If you notice, we give it X, which X? This X, and we give it Y, this Y, always in that same order. Then we specify the size of the test set. So what that means is, what percentage of the data should be given to the test set. And actually, we can also randomize the sample. So there's 150 samples here in order, right? But it can randomize the rows and then for both X and Y, and then split it. That's really nice. And you should always, want to randomize things like that. So I guess we can do 0.3. What is 30% of 150%? Well, we'll see, I guess. But I want about 120 for the train set and about 30 for the test set. So we'll see that. Random here, if you define random state and you give it a number like this 42, it means that every time it's going to randomize the same way. And this is so that you can replicate results, like from one experiment to another. This helps you to always be able to replicate. But if you just leave it, without that, then it's going to change every time. All right, so notice that it produces in this order, the X train, the X test, the Y train, the Y test. So you always want to write this out like this. Okay, so let's go ahead now and run it. Oh, error. Oh, train test split is not defined. Yes, because we have to define it up here. We have sklearn now, but we don't have the library, the module defined. So we have to do this here. Okay. So from sklearn, model selection, import train test split. All right, no errors. So now I can go down here. And there you go. That's it. Now I've created my X train, my X test, my Y train, my Y test. So now I want to view them. And in particular, I'm just going to view the shapes. So you can see I'm just going to copy this. And so basically on that 30% split, 105 of the iris data samples are allocated to the train set and 45 to the test set. Got it? So I usually like to think in terms of 120 and 30. So that might be then a 0.20 split. Yeah. So you can see now 120 samples of the 150 for training, 30 samples for testing, and that's the same for the labels, 120 and 30. Got it? Any questions? Great. So now that we have this, we have our data sets, right? We have our data sets ready. All the data is prepared. And now here, what the next step would be to normalize, standardize the data. I'm not going to do that for this example to keep it simple, but in the future, I will start adding that because it usually improves the results, okay? So the next step now is basically to test our models. So this should work, except that we haven't defined the Euclidean distance, I think. Yeah, so we're going to need that, and we need to talk about that. So I'm going to move. Yeah, here we had just done this. So I'm going to add that now. All right, so I'm going to leave it commented out for now. We'll come back to it. All right, so we got our data. Get rid of one cell here. I'm going to get rid of this. All right, so the algorithm then is this one. Now we have to start running this data through this function, okay? That's what we're going to do next. So I'm going to start here. So you can see for test X in X test is this one here, right? So before we do anything, let's just print it. Before we actually run it through the algorithm, let's just print each test X. Test X, there we are. And I like to do this sometimes. Input, and that just allows me to hold the program, kind of like when you first learn a program, you were holding your programs. So let's do this. You can see it's giving me 6.1, 2.8, 4.7, 1.2. What is that? That's the first sample of the test set of the 4 features of a plant. this is what is going to go into the model, and the model should tell me, oh, that's Setosa, Virginica, or versicolor. But it gives me just a number. So 0, 1, and 2. And then I have to interpret that. Got it? All right. If I hit enter again, it shows me the next one, and so on, as you can see. So I know this is working perfectly. So I'm going to stop that. So I'm going to remove it now, as I was just debugging. Here, then, what I would do is I have this KNN predict, and I'm going to supply to it the test X. So now this will go, and with this print statement we may need to change, but let's go here. It goes to the algorithm, and it's going to calculate the distances. So now I'm going to comment out some of this. All right. So the test sample comes in. X train is already defined globally. It's this one, right? And the values in X train are also vectors of 4. So I'm going to take 4. So I have test X, and now I take 4X in X train, and I take those two values, and I need to send them to the Euclidean distance function. And the Euclidean distance function takes the distance between both of these points in the vector space of 4 dimensions. And it's just going to store them in the list distances. Okay? So this should almost work, I think, except for one issue. We haven't finished the Euclidean distance function, which is this one above. So this takes two values, and it performs some math operation to calculate the distance. And this is what I provided basically in the link here, the math of it, right? So basically this captures the whole thing, right? Pythagoras came up with this idea, right? You guys probably remember this. The sum of two triangles in a rectangle triangle, something like that, right, is equal to the other one. So I wrote it down here. I have it. So he came up with, where is it? It's probably this one. So this explains the whole algorithm. Maybe it's below. Oh yeah, here it is. The theorem states, the Pythagorean theorem states, that given a triangle, the sum of the areas of the two squares on the legs A and B equals the area of the square of the hypotenuse of the triangle. So this idea here, right? So what he's got. So it says the sum of the areas of these two equals, I guess, that area, right? That's the actual theorem. So that's written down here. The area of something is a square, right? For a square, for squares, basically. So then it's saying a square plus b square equals c square. Do you guys see that? That's the same as the theorem. And if you kind of like rearrange the terms, then it basically gives you this formula. Because to calculate A is just when we have points. So here we have P1, Q1, P2, Q2, which are the features, right? So then to get A is just P2 minus P1. To get B is just Q2 minus Q1. So you can see that P2 minus P1, Q2 minus Q1 equals A and B. And essentially from here, we derive the formula. This is for the case that is two-dimensional, but this extends to any dimension. Like if we had PQ and R, so then we would just say this and this plus R2 minus R1 squared. And if we had yet another axis, K, then K2 minus K1 square, and so on. Do you guys understand? This is something you know from high school. Right. All right. So you learn this. But what's really neat about this is, think about it. This thing that you learn in high school is actually used in machine learning. And that's the essential, the formula. Yeah, go ahead, sir. You're having a problem with reading the file? Okay, I'll go back to that. All right. So anyway, this is the background, okay, of the formula. So it comes from Pythagoras. You have the measurements there, the representation of the theorem, and then how it translates to the equation that I'm about to input. All right, so I'm going to go over here. So let me just finish this, and then I'll address your question. So you can see the actual equation is right here. It says so it's going to be V1 minus V2 square. That's essentially P2 minus P1 square. But we have several. So the formula just generalizes by saying the sum of these. So because, so it's V1 minus V2 square, the sum of them, and then we take the square root of it, which is this one. Okay. So these are I actually need to drill down here a little bit more because this is something important that you need to understand about vectors, that V1, V2 are actually 4 and 4, right? So it's comparing the first of V1 to the first of V2, the second of V1 to the second of V2, the third of V1, and so on. So it's doing that operation as a vector, right? And so I will print this out in a sec, but it's important that you understand that. All right, and then we sum them overall, and then take the square root. So this is going to be our function. V1, let's implement it so that it works, and then we can take a look at what I mean. And this should actually just be it. All right, so now we have a working Euclidean distance that we can use in this context here. Make sense? All right, so before I run this, let me go back to, what's your name? Brian? Ryan. All right, Ryan. So your issue is that you couldn't read, so you're stuck probably, you're not getting this, right? Yeah. So your problem happened here. So go to this part of the Jupyter Notebook. Do you see the file iris in there? Iris.csv? When you click on it, does it look like this one? Okay. All right, that's interesting. And then you go to the code. Did you do PD read CSV iris.csv header? Oh, it's not. It's gonna go. All right, so his error is that PD is not defined, which means he doesn't have it at the top. So Ryan, go to here. Do you have this? Import pandas as PD, where you have your libraries? Did you run it though? Go to go to this cell and just add it in there, and then run that cell. You need to like bring it into your environment. Do you know what I mean? Did it give you an error or did it work? So it means that it just loaded it, right? Oh yeah, there it is. Yeah, but that's why I recorded. Yeah, so eventually it says. All right, but you got it now, right? Okay, perfect. All right, guys. I'll post this video, of course, in the class today. Any other questions? Nope. All right. Everyone with me so far? All right, perfect. So yeah, this is your first algorithm, the easiest, I should say. But the other ones are not super hard either. So we did all of that. We did all of that. That's fun. We've defined Euclidean distance. So now hopefully it works. So let's see this through, and then in the end, or maybe next week, I will come back to the Euclidean distance in a little bit more detail because we have a few minutes left, so I want to finish this algorithm. Okay, so let's run this. This cell has not run, so let's load it in memory. No errors. Okay, now we can run the KNN predict. Basically, it's just going to give us distances and print them, essentially. So run it. Now we are going to run this one here. And there you go. It worked. For every sample, so let's actually do this another way. I'm going to put a halting input function here. So input. So this will hold just for the first sample, right? And test X. And you can see that it's giving me how many? It's giving me the distances between that test sample and 120 samples. Well, we can test that. Put a ling, indicate length. Oh, it gave me an error. This KNN predict. KNN predict. Oh, it doesn't return anything. That's my fault. A 120. There you go. So it basically calculated 120 distance. Do you guys get that idea? So you take one test sample of vector of 4, compare it to that vector of 4, that vector of 4, that vector of 4, that vector of 4, takes the Euclidean distance, and now it's got 120 distances, essentially. So we're there, right? We're getting there. Now what do we need to do? What's the next step? I need to take these 120 distances and sort them. But I'm going to use arc sort, and instead of returning the actual distance, I just want the index. So I want to know that, let's say that this is the shortest distance, actually, right? So when we sort it, that would go in the front. So I want to get that index, and that index is actually what? 120 or 119 because it starts at 0. You guys see that? So it takes the original index, and that's what it gives me. Why do I need that? Because I'm going to look that up in the y vector. So that's the idea. All right, so let's stop the program here. Let's remove the input, get rid of this length here, get rid of that. So go back to this code. We don't need this or that. We just needed the distances. Now we're going to arc sort them. Right? So we sort by distance, but return the index. And then we just want the 5 closest. That's it. So we can print this actually. Print K neighbor indices. Okay. All right. So we have that. Let's run it. Did you notice what happened here? So now for test sample 1, these are the closest indices. For the next one, the closest are 48, 14, 94, and 114. Remember, these are no longer the distances. They are the index in Y. So now we go to Y and just extract the corresponding label, and boom, we have them. That's it. All right, so for every test sample of the 30, right, I've been able to figure out the 5 closest samples in the train set. Here I'm returning the index of those, and now I just need to extract those from Y. Yeah, do you have a question? That's right. That's exactly right, because we did it here like that. We said NP arc sort. So it takes all the different distances from that sample, puts them from in ascending order, right? From smallest to biggest, but it doesn't return the value. It returns the index, because that's actually what we needed. So these are like the conveniences of NumPy and Torch designed for data science. All right, so we got that one done. And actually now, all we need is to extract the labels from the Y vector. Since we have the indices in k-neighbor indices, then it's pretty straightforward. We have 5 for each, right? We have 5 for each. So we just say for each one of these, we'll say for I in k-neighbor indices. So each of those 5, so we grab this one and this one and this one and this one and that one, and and so on. And we look them up in Y train, right? So we'll say, okay, in Y train, I need the label for index 79. And then I need the label for index 90. And then I need the label for index 39. And I'll have all those labels. So now we're just going to repeat the same thing, but we're going to print labels instead of the k-neighbor indices. So print labels just like that, right? So let's go ahead and get rid of that actually. So run, and there you go. You can pretty much now at this. So for the first sample, what is it essentially? What label is it? 1. What about for the next one? 0. There are some that is very clear cut. In other cases, we do have some like this one. There's some 1s and 2s. So in this case, which label is it? Is it 1 or 2? You go by majority. That's why you pick. So it's going to be 1. Exactly. That's why it's a good idea to pick uneven numbers. In this one here, okay, obviously 2. And so on. So this one, obviously 2, and so on. So now all we have to do is take the average of that, or count the, count the winning, the majority, and return that. So we have a nice little function for that, which is should be here. Okay, so we've done distances, and then we probably can just use that counter. We'll need to import this library, which is from collections import counter. So we're going to give it labels. I'm going to leave this just so that we can corroborate that it's working. So we're going to take just the most common from labels, and it's going to return it into most common label. So I'm also going to print that out. Just like that, just so that we can corroborate. I do need to add that library though. So and that's like a Python library. So we don't have to install it, I don't think. So from collections, import uppercase counter. So let's do that. All right, it worked, no issues. And now let's just update KNN predict. And let's run it. So essentially, this is telling us that there were 5, but it's returning the value that we want. So all I need to do here is it's a tuple, right? So it's a list that contains a tuple. If you look at the data structure. So I'm going to have to do, it's a list. So I get the first element and then probably the first element. Let's run it. There it is. So now I've got the label. So is it correct? Well, let's verify, right? So this one should be all ones. It is. All zeros, all twos, all ones. So these are matching. Now, how about this one? 3 ones and 2 twos. So 1. That's correct. This one, yeah, only, yeah, so mostly are twos and returns twos. This one, 2. Yeah, that's it. What do you think? It looks correct, right, guys? Yeah, and that's basically it. So now you built your very first machine learning algorithm, KNN. It's a vector space, geometry-based algorithm. That's it. Good job. Any questions? Right. So this is so you can add this to your your toolkit of algorithms that you can apply. If you're doing the WECA homework, if you remember, IB5 in WECA is KNN. So now you know how that algorithm works essentially. It's you can try this. It's a powerful algorithm. Sometimes really what matters is the data, right? So if you have good data, good features, KNN may be all you need. And you can implement this from scratch. You can literally write the code for this in a browser, right? So you could write it in JavaScript maybe, or you could use PyScript and write it in Python and then run it on the web, essentially. So, on your toaster, you write some C code, it can do KNN. You know what I mean? Look, you can write it anywhere, and you're not limited by any libraries or anything like that. So sometimes that's useful. All right, so I think we pretty much completed this. What we might want to do is we have 6 minutes left. So let's see if I can do this in 6 minutes. The last part of this is we want to measure performance, right? So here I don't know if it's doing well, but I do have the real label of X test. So if you remember, I'm giving all the samples in X test and it's predicting a Y for that sample. But I do have the real Ys for X test, right? They are in Y test. So Y test contains the actual labels for X test. And what we're doing right now is we're running X test through the KNN algorithm, and the KNN algorithm is predicting Ys. So essentially we have Y-pred and we have Y-test, and we want to compare those two. So I just need to create some kind of a list of this for each test sample. So I'm going to do something like here probably. Yeah, I'm going to return. All I need to do is return this one. I return that. And so I'm going to have a list here called YPred, like that. And I'm going to then, because it's returning now, I'm going to change this a little bit. I'm just going to say my YPred, right? It returns a label. Oh, actually, let me say YPred list here. So then YPred list dot append. And I'm going to add to it the predicted value. I was debugging, so I was using all these print statements, but I don't need them anymore. I know it works. So now I'm going to repeat this. It did it, no errors. So now let's print this one. No, it's actually, sorry, YPred list. Should be. There you go. Those are the predicted values. There should be about 30 in there, and we need to compare these to the Y-test values. So how do we do that? That's the last part of it. How to measure performance. We are going to need these performance metrics, which are exactly the same ones that you're using in Weka. So I'm going to go up here from sklearn once again. From sklearn.metrics, I'm going to import the confusion matrix, the precision score, recall score, accuracy score, and F1 measure. And these later, I need to drill down into the theory behind them. But for now, let's use them as we are using them in Weka. So I have a really nice function for this so that you don't have to worry about coding this up. So it should be here. I always use this, even for PyTorch problems. There it is. So all you have to do is grab this function. And it takes in Y-test and Y-pred, right? So Y-test and Y-pred. We have to make sure that they're in the right format. If you notice, one is a list, the other one is a NumPy array. So that may be an issue. But this will just print the results, similar to how Weka does it. So you can see here, I already have the code. I'm going to convert the list into NumPy, essentially. And that's it, guys. That's pretty much how this works. So I take my little list over here, YPred list. So I'll change that name. YPred list. There you go. I invoke numpy np.array. That changes the Python list into a numpy array called YPred, right? So run that one. And now the moment of truth, right? So did my machine learning algorithm work? So I'm just going to do this. So I invoke print stats performance, which is this one, and I give it Y-test, Y-test, Y-pred, Y-pred, and it's going to print out all the metrics. And there you go. Done. What do you conclude about this machine learning algorithm? Is it bad or is it good? Huh? Really good, right? It's really good. Iris is easy. Iris is an academic type of data set meant to illustrate all these things. But once again, accuracy is 100%, precision is 100%, recall score is 100%, F1 and the confusion matrix. Remember, we want everything on the diagonal. Now I can intentionally make these metrics be worse by simply giving the model less data. So hopefully. So what I mean by that is I can go here and make the test set a little bit larger, like say 0.40. So it has less data to work with in the train set. So we should get a few errors, right, by doing this. So let's see if it works. So all I have to do is repeat this. Notice now I'm using 90 samples for training and 60 samples for testing. So in terms of probability, I'm more likely to get errors now. Euclidean distance, KNN predict, YPred, right? So we got our predicted labels, got our metrics function, NumPy array. There you go. See, 98%. And I got one error, right? In the last row here, you can see one misclassification, but it's still pretty good. All right, so that's it. That concludes your very first machine learning algorithm. So now you know one, and you know how to implement one from scratch. Like I said, you can implement this in JavaScript even, probably. Okay, so let's end the video here. We're going to end the class. You have your WECA homework. Please work on that. I don't know if I'll assign a homework associated with this, but this was the first algorithm. Next Monday, I will probably drill down a little bit more into that Euclidean distance again. And then we'll look at our next algorithm, which will likely be maybe hot field networks. We'll see. All right, guys. So let me stop the video here. And if you have questions, I'll answer them in a sec.